So good afternoon, everyone. Good to have you with us now for this afternoon session where we concentrate on some scientific presentations and talks. As you can see, we've got chairs here. Now, we want to focus on three main themes this afternoon. One, Rosetta orbiter science, Rosetta comets and asteroids, and then Rosetta and the Philae lander science. Let's start with the orbiter science, and for that, please welcome the two scientists that will join me now on stage. If you care to, you can also give them a round of applause. That always goes down very well with people. Dr. Holger Zirks and Dr. Joel Parker. They will take a seat here, and I will then introduce them in a bit more detail. Now, Dr. Zirks, he's the principal investigator of OSIRIS, I was told it is pronounced. That's the camera on board of Rosetta. He works at the Max Planck Institute für Sonnenforschung, that's here in Germany. And Dr. Joel Parker, he's the director in the Planetary Science Directorate at the Southwest Research Institute in Boulder, Colorado. I hope this is correct now, because yesterday I had it all mixed up, but that hits it now. And he's also the principal investigator of the ALICE instrument on board of Rosetta. Now, before we talk about these instruments, let's first clarify one question. We touched a bit on this one this morning with some of the experts we spoke to in the main control room, but why do you think it is important for us to actually go to a comet?
Well, that's a very good question. People ask that all the time. It's important to go to the comet for several reasons. We've flown by comets, we've crashed into comets, but we've never lived with a comet. And those other missions were, brief encounters. What we're looking for is more of a long-term commitment here. So,
like a marriage.
That's right, exactly. So it's going to be a marriage between Rosetta and the comet. And we need to see how the comet evolves over its lifetime. And this is important because what we see from the ground, say from observatories on Earth, is the large-scale behavior, the big picture, the coma, the tail. But what really drives the comet, the real heart of the comet, is the nucleus. And we simply cannot see the nucleus. Even with the Hubble Space Telescope, we don't have the resolution to really see the nucleus. But that is what Rosetta is going to give us. Mm-hmm. Rosetta is going to be there at the comet, and it's going to allow us to translate, basically like the Rosetta Stone, allow us to translate what's happening at the nucleus that drives the bigger activity of the coma and the tail.
And it's apparently, from what you tell us, very important for scientists, maybe for mankind, to learn a bit more about that. Or Holger, what do you think is the explanation for our interest in comets in that way?
So my view at it, it's true. We have seen a handful of comets by flyby spacecraft. We have seen lots of comets from Earth, and so Comet Ison recently. So it's touching the people. It's there on the sky. It's common to all of us. So we want to learn about it. But beyond that, I think it's so true. Comets are cool. So literally. So comets are so cool. They store the stuff we were built on. It's not only accretion and origin. It's the story about us, and I think this is at least most important to me, that it tells us about the story of how the solar system, how life evolved, hopefully, to some extent, the bigger picture.
This big question of mankind.
Yeah, prebiotic, if you want.
Of course, in order to do so, Rosetta is equipped with quite a number of interesting instruments. I think in total 7 instruments are on board of Rosetta. And then, of course, there's the lander that has even more instruments on board as well.
It's 11 big instruments, plus the lander with the whole suite of instruments.
And you are involved with instruments on board of Rosetta. One is called ALICE, and the other one is OSIRIS, which actually is a camera on board of Rosetta. Now, we're all familiar with how cameras work. How can we picture a camera on Rosetta? What's its function there? I mean, it's dark there in space. What kind of pictures will it take?
First of all, it's not a camera you really want to carry around and take snapshots. So what I see here is not possible with our cameras. So it's a set of boxes, and it's 35 kilograms you can't really carry around. The technology, though, is, well, it's a 4 megapixel camera, which is not what you carry on your cell phone nowadays. Still, these are wonderful chips there, wonderful CCDs that are made for science, so you can really get calibrated data and the highest resolution you can carry with the spacecraft at that point in time. The resolution you get is astonishing, knowing that the mirror, so the system, it's not a Hubble Space Telescope. Yeah. It's a mirror that your kids have at home to look at the sky, to see a comet or a planet or or look at interesting stars at the sky. So it's a 10 centimeter system. So coming back to Osiris is 2 cameras, so we want to do both. We want to look at the nucleus, which is unresolvable from ground. So from ground, the center pixel of all the stuff you see is 1,000 kilometers.
And how close do you hope to get with Osiris?
We will get to all the mission will happen within the center pixel of the ground observatories. So all the mission, even the long excursions, will happen within the center pixel. So we want to go close. Close means 100 kilometers for the global, what we think is the global scale, and then we want to go down to 2 kilometers to the surface, where we get the real view at the surface and the activity, the stuff that really goes on there on the surface. And it was one of the guys around here that said, well, this is so cool. It's like opening the window to your backyard. So we get something like 2 centimeter resolution. So you can see from your window at home, there is a little boulder, there is a new plant grown overnight. So this is the resolution we expect.
That's the kind of image that we can expect to get from Osiris. But
Yeah.
you touched on a very interesting topic here, because you mentioned, of course, that the technology has advanced, certainly in the last 10 years, and that also goes for chips and photographic technology. And it will be the same with an instrument like ALICE. All these instruments have been developed way before Rosetta was launched into space. So how up-to-date is ALICE, for example?
Well, a lot of the instruments, of course, as you said, they were built long ago to be launched, and they've been in space for 10 years. A lot of it is still very cutting-edge technology. Even though there are some aspects we could improve. If we were to launch a new mission, we could have cameras and spectrographs like ALICE that have perhaps better resolution, better sensitivity, but it really is still a phenomenally cutting-edge and advanced laboratory. 2 laboratories that we're basically sending to the comet. Right now they're showing an image of ALICE, and you can see here ALICE is a camera you could probably carry around if you wanted. It weighs about 3 kilograms, so you can see the size there. And it uses only about 4 watts of power, 4 to 6 watts, which is, you know, a night light bulb. So these are still very advanced instruments that do a lot for very little power.
Like what? What can ALICE do in order to make that mission a success?
Well, ALICE contributes basically taking ultraviolet light and spreading it out into a spectrum, like, you know, a rainbow, except in the ultraviolet. And in that spectrum, you have certain lines, basically fingerprints of the different chemicals, the elements and molecules that make up the gas that you're looking at, or the surface. So ALICE will be able to identify some of these chemicals that we can use as temperature indicators, both temperature of the comet, but temperature of when the comet formed. And that goes back to the whole case of the origin of the comet and where it formed and how it formed.
Now, that seems to me quite a lot of data that is Alice collecting, but also Osiris obviously taking lots of pictures. Now, when I have a pretty advanced computer at home, but when I send an email to a friend or to family and I want to attach some high-resolution photos, there is very soon I reach a limit and the email just won't go and say, you know, too much data, you have to compress it or you have to simply send less. Now, here we're talking about huge data that's being collected, somewhere 800 million, 700 million as it eventually approaches the sun again, kilometers away from us. How do these instruments cope? How do we receive all that data?
Well, I would say we have the same problem. So we have about 60,000 images in the pipeline, so about half and half with a wide-angle full story observation and the nucleus-centered high-res observation. And we know we can't get them all down in full resolution. So we use modern technology in compressing images. We have the way of binning, so reducing the size of the images on board such that we even ever have a chance to get them downlinked. So we are very grateful that ESA has expanded the capability to receive those images. So we have 3 wonderful large 35-meter antennas. And we will get additional support by the DSN, which is really, really a step up in data rate. So the takeaway message is we won't see all the 60K in full shebang. So don't expect every day 1,000 images coming down. This is not Mars and a megabit line. It's a telephone line down. And,
Joe?
I just also wanted to add to that. A lot of the planning is what makes it possible to bring down all these data. So unlike your email where you may just send it off, this is where you have a committee of people deciding what emails are going to be sent. So you have all the PIs working together, finding an agreement for who sends down what data. And you also have an excellent control team here that manages the data stream. So it's as if before you sent your email, everyone agreed on what emails were going to be sent. And that's how you coordinate it and you make it fit within the narrow pipe that you have.
Well, last question before I open it up. And if you have any questions, we would like to take those then as well. Obviously, all these instruments, just like Rosetta itself, were now out there in space for the last 10 years, and they were inside a spacecraft that was asleep for 3 years. So when will we know if Osiris and Alice are well and ready to start working?
You start. Osiris is on first.
Osiris is on first. So stay tuned, it will take a little while. So first we have to get through spacecraft wake up, completed, and check out. And then the power has to raise, we have to get closer to sun such that we can afford to get the high power units really switched on. So Osiris is going to be switched on March 17, and we have something like 5-6 consecutive days to really go through checkout. And so one day after us?
One day after, Alice will be first turned on, and that's basically going to be a on and off. We turn it on, check the memory, turn it off, just to make sure Alice's brains still seem to be there. And then roughly a week or so later, we will start going through a more detailed calibration checkout, slowly ramp up, make sure Alice is awake and healthy, same with Osiris. And then basically when the checkout's all done, end of April, something like that, then we get to start looking at the comet.
At the end of the checkout, there is no way out. We'll have to open the doors of the camera. So it's a checkout. So we open them, close the doors, but we can't really help but take an image. And we are inertial to pointing. So we are expecting at the end of checkout to have an image of the comet already. It will be sub-pixel, not high resolution, but we hope to... we know it's there,
yeah.
and can hopefully share the first image post-hibernation with you. So we took an image of CG just a couple of months before hibernation. So we targeted CG in March 11. And
CG is, of course, what we also call 67p. So
yes,
this
so the
in case you don't want to say
name,
Churyumov Gerasimenko, you just say CG for short.
And that helps a whole lot in communications. So we took a long exposure, and so 13 hours of exposure chopped in 52 images, 15 minutes each, collecting single photons basically from a dark spot of 4 kilometers size, 160 million kilometers away. And if you flip one ahead, we saw it in March 11 from such a far distance. And I hope we'll see very soon the first image of CG post-hibernation, and with a long exposure, hopefully already the first sign of activity, which is the core of the story around CG. We want to see it active and come up now.
Yeah, that's what
only
we're there
wake
for.
Up, it's also come up CG now.
Now then, I'm somewhat blinded here on stage, so if there are any questions, then please raise your hand high above your head so I can see that you would like to ask a question. Right now, I don't see an arm flinked up into the air. Oh, I can see you better now. All right, now a smaller sign will do, but I don't even see a smaller sign. You're still breathing, though. Good. Then we still have 2 or 3 minutes left. So if you're okay, I would like to wrap this session with one, if you like, somewhat more philosophical question, because obviously what Rosetta is doing, a lot of it has never been done before. So there isn't really a blueprint, and that also goes then for the entire mission, its instruments, etc. So how do you prepare for the unknown?
Well, that's what you need to do, and you have a wide array of instruments as we have on the spacecraft to try to look at as much as possible. I mean, part of science is figuring out what is unknown and what is unknowable. And there's a lot that's unknown, but we can know about it if we just look at it the right way. So we send a lot of instruments on the spacecraft that can look everywhere from ultraviolet to visible, infrared, microwave, all the way out to radio, that sniff the gas, that test the dust, that check plasma, all these things to try to see what we can find. There are a few things we expect, but the fun part will be the things that we don't expect.
Okay, the unexpected. Well, thank you very much, Holger and Joel, for filling us in on the instruments and also your take on the mission as a whole. Thank you for your interest. We will take a short break. We'll be back here at 3:15 Central European Time, or 2:15 GMT for those watching us out there via web stream. And that's when we will check in again with Andrea Accomazzo in the main control room to get the latest update. For now, thank you very much, and a round of applause for our 2 scientists. Thank you. So here we are again. If anyone wants to join us from outside, because as I promised, we will now check in with Andrea Accomazzo in the main control room to see what's been happening in the meantime, whether he already has the first idea where that signal we're waiting for could be, or how long it could still take for us to get that first signal. So let us see if we are connected to the main control room now. I presume we should get a picture up here on screen. There we are. Okay, then I turn to this side. And can I see Andrea there? Very difficult through the glass panel.
Yeah.
Andrea,
I think I'm connected right now. Can you hear Monica?
Beg your pardon?
Can you hear me?
I can hear you.
Good.
Yes?
Hi. Good afternoon again to everybody.
Ah, yes, I can see you now as
Good.
well.
Excellent. Okay, good.
Oh, there you are. Oh, that's much better. Now we have a clear view of you. Andrea, tell us what's happening.
Well, we have prepared now all of our systems here on ground. Our software systems are in place. We have already talked to the colleagues in the States that will be activating their big antenna to monitor Rosetta first in California. And the antenna is being prepared right now. So in 20 minutes from now, a bit shorter than that, we will start tracking the portion of the sky where Rosetta is meant to be. We do not expect to see a signal at that point in time. It's only in 3 hours we expect to see a signal from Rosetta. But I can say that all our systems are ready to go.
Okay. But it could be also a bit earlier, couldn't it?
Well, there are extremely remote chances that the spacecraft wakes up earlier than planned. Technically, it's possible on board the spacecraft, but we have never seen anything like this on any of our spacecraft with similar onboard computers, similar clocks. So I rate this as it's negligible, but technically it can happen. There's nothing on the spacecraft preventing it completely.
It would be another world's first. Andrea, before I let you go, because I'm sure you're eager to get back to your instruments and keep an eye on that possible signal somewhere out there, your father has not only built this model that we see there in front of you, it's also his birthday today, isn't it?
That's correct. That's a big surprise indeed.
Yeah, but isn't that great to coincide with the big wake-up event? That's a great birthday present. Well, wish him a happy birthday from us, Andrea.
Thanks a lot. I want to mention that we also have a flight control team member that has birthday today, Zarmel. She will come on shift later on, so it's a good coincidence for both.
Okay. Well, Andrea, we'll be checking in with you again at 4:45 for the latest. Okay, thank you very much.
You're welcome. Bye. Talk to you later.
Okay, bye. Right, now you know the latest, and in about 10 minutes we will have 3 scientists here on stage again to talk about comets and why we chase them. So if you're interested in that or want to ask questions yourself, then stick around. Okay, see you in a bit. All right, thank you very much for sticking around. Welcome back. And as you see, we're ready for our next session now with 3 experts. If you have your hands free, then please put them together to give them a warm welcome. Worked wonders for those before, thank you. So, who do we have here? Right next to me is Dr. Gerhard Drolshagen. He's the Space Situation Awareness Program Manager at ESA. Then next to him is Dr. Norbert Perler. He is the Program Manager for Space Science Missions at Airbus Defence and Space, former known as Astrium, now Airbus Defence and Space. And to his right is Dr. Gerhard Schwem. Up until very, very, very recently, he was the Rosetta mission manager at ESA, and he only just retired, but he's still very, very much part of the mission, and he's certainly here to give his advice and to consult everyone, which is great. And I would like to start with you for that very reason, Gerhard. There are 2 Gerhards, so I will always look you deep in the eye so you know which Gerhard I'm talking to. Gerhard, in this session, we want to focus on Rosetta, comets, and asteroids. Let's stick with comets first of all. Obviously, we heard it this morning already. There seems to be this huge fascination surrounding comets. Mankind has always been wondering what these heavenly bodies could be. Are they a threat? Are they a sign from God? Is it some superpower? And despite all the science that we have now, and we can explain what these things are, the fascination hasn't really died. How come?
That is really clear that the fascination has not died, and we have seen that just before Christmas when Ison was to be seen by naked eye. Everybody was fascinating. What if this comet will live up to the expectation to be a very bright comet? It didn't, and it came close to the sun and then disappeared, was disrupted, but everybody was really, so to say, misery with the poor comet, but it showed how fascinating these objects are. It also showed that with Ison there were a lot of predictions, and it was still open till the end what would happen. It shows that it's very important to study a comet from close by. But as you said, comets in the history of mankind were very important because they were seen as signs that you get a new king or that a war is there or diseases and all these things. And I think we show here one of the images that is from 1910 when Halley came close to the Earth that shows that 100 years ago, this threat was still felt with people. So we have progressed in our understanding, but still comets are a mystery to us, and scientifically they are so fascinating and we have to study them.
So the Rosetta must be a dream come true for you.
For me, Rosetta is a dream come true scientifically, and I also, there's also comets. One of my pet talks is to comets and the influence on the quality of wine, because that was also something. So comets are used for everything and for all. And what I show here, and I think that's very important, that comets are, so to say, bringing to us the most primitive material that we can study with our current day technologies. Comets are, so to say, the messengers that bring material that we had at the beginning of the evolution of the planetary system. That's in the comets that we want to study, and that gives the big bridge to today.
Some great pictures there, Norbert. You can't wait for your question. You want to say something straight away. Off you go.
Just try to summarize what Gerhard said, namely, I would call the comets the guiding fossils for our planetary system.
Uh-huh. That's interesting, but fossils
and therefore,
sounds very dead. Then why don't I go straight to you? Because I also know that you like another quote, which is not from you, but you used it in one of the talks we had beforehand, and there you said that comets are like cats. They have tails, and they do what they want. That's very different from a fossil.
Okay, that's a living example of a comet which could not forecast it, and it was Gerhard who mentioned what happened with ESOC. He was supposed to be the comet of the century, but it vanished during the perihelion at the Sun, and therefore still I insist on the character of a comet as guiding fossils for our planetary system, and that's the reason why comets are so interesting for space historians.
But not only for space historians, also for someone like the Gerhard next to me, who actually has not been involved with Rosetta, but as a SSA project manager, you obviously keep an eye on whatever is out there and could affect the Earth. So you did keep a keen eye on this mission as well. What significance does Rosetta, and especially the comet it's watching, have for you then?
Well, we look at a different aspect from the pure science of these objects, and that is what happens if they come very close or too close to Earth. So we call these near-Earth objects if they can approach Earth up to 45 million kilometers. And in the Space Situational Awareness program, we look at the risk from space weather, from these near-Earth objects, and also from orbiting satellites and space debris. And so we try to find out what is the risk, because we know...
What is the risk? That is a very good question. Everyone here probably has seen the film Armageddon with Bruce Willis. So imagining one of these comets, let's say CG 67P, whichever name you prefer for the comet that we're looking at right now, decides to actually pay Earth a visit before it heads all the way to the Sun. What is that? How likely is such a scenario?
Correct. First of all, one has to learn about those objects. That's also why we are very much interested in Rosetta and the results it will give us from comets. If you look at it from a risk point of view, asteroids are more dangerous than comets. Asteroids come from the asteroid belt between Mars and Jupiter, while comets come from further out, as we have heard. And right now, if you look at these objects that really come close to Earth, it's more than 10,000 asteroids known that can potentially come close to Earth, and only 94 comets. And those objects have hit Earth in the past. We have impact craters found on Earth. And just last year, there was an object now believed to be only 19 meters in diameter.
In Russia.
Which exploded in the air over Russia. And you can see a picture here of a fireball. And it caused injury on the ground. It was only 19 meters. So you can imagine if a much bigger object would hit Earth, what damage it could do. And we try to find those objects, to assess the risk and to measure them. So we have to learn a lot, and then we also start to think what one could potentially do against them.
But
the good news is indeed that we know about thousands of objects larger than 1 kilometer. The bad news is that about factor of 10 are unknown.
okay. If asteroids are so much more dangerous to us on Earth, why do we study comets instead?
Because comets are much more important from scientific point of view.
No.
and much more fascinating. But comets are much more primitive than asteroids. I think that is the key point. Comets really have the material. If we get to material that was here in the pre-solar nebula, then we have to study comets. That's what we still think. And I believe after Rosetta, this will be even more confirmed.
Okay.
And also comets, give us a clue to the infant state, to the infancy of our solar system. And we want to see what material was there. Were there complex molecules? Was there water that perhaps was brought by comets to the Earth? Is still one of the possibilities. But I think the real big point is to see how complex the material is in comets, and and to understand how the planets evolved out of this. And therefore, for me, scientifically, they are more important. They are not as dangerous as the others.
It just beats the others.
If I might add to this, I would say asteroids are more dangerous because there are many more of them, but most of them are smaller. But comets, if you just take one object, they are bigger, typically several kilometers in size. They are faster moving than asteroids if they would hit Earth. And as we heard before, they are completely
Called Don Quixote, together with the US and Russia, presumably in order to learn a bit more about near-Earth objects, some of which could be comets as well. However, I did stumble over the name Don Quixote, to be perfectly honest. Why that name? Don Quixote fought windmills. What does it tell us about that study?
Okay, in order to be clear, we performed a study called Don Quixote on a phase A level for ESA years ago. And that was Don Quixote having 2 spacecraft, 1 orbiter and 1 impactor. And the impactor was supposed to deflect the object which was ahead to Earth. And at this time, we have, so to speak, some sort of extension of that study, namely on behalf of the EU, we investigate methods to mitigate such near-Earth objects with different methods, not only by impacting and deflecting objects, deflecting objects by impact, but also by gravitational attractor or by some explosives close to a dangerous object. And that study is running this time, and it's a worldwide study team involved.
Okay. Now, let's leave all the danger behind and let's leave Earth behind for a moment. Concentrate on Rosetta again and its comet. I mentioned earlier that Rosetta is obviously now traveling for some 10 years, been asleep for 3 years. We all change with time, and even objects change. They don't remain the same. So is the Rosetta that left 10 years ago still the same Rosetta, or do we have to expect some alterations there? I mean, it's been exposed to an asteroid belt, maybe external radiation. We don't quite know. How well is Rosetta prepared to deal with all that?
I think Rosetta is still and should be the same, otherwise there would be a risk that it doesn't work as it should. But we have, when Rosetta was designed, all these effects were taken into account. The electronics is, so to say, radiation resistant or radiation hard. The spacecraft was built to at least work for 12 years. All the technology used is based on experience, for example, with communication satellites that work for 12 or 15 years because they have to bring back money. And all this was thought about. We also, the solar arrays, and as we go closer to the sun, they were also designed that even if they degrade over the 10 years, which to some extent they do, they should still provide, also at this distance now where Rosetta is, enough power. And the instruments were built like this, that the electronics should work. So this was taken into account. So the spacecraft should be the same. the question we might ask with our instrument might have evolved, because 10 years and 10 years of comet science, a lot of things have happened. But still, what we can demonstrate is that Rosetta, the importance of Rosetta has not changed. Everybody admits that this is the next important step in cometary research. So this has been done. I think we have had a good vision. We knew what we would do, and I think that will hopefully show in a couple of months.
There was also an interesting thing when you said that things change. Also, the questions. I mean, when Rosetta was designed, when the instruments were designed, when it was launched, there was a certain set of questions that you hoped to get an answer for. Are the questions still the same, or have some of these questions maybe been answered in the meantime or altered?
I can say the questions are still the same, and I have to admit that. I said this morning, after 10 years, where I always said, you know, we are going to measure this, we are going to measure this. Now we will measure it, hopefully, and I don't have to repeat that. But the missions we had in the meantime, because the Americans had a couple of these flybys at other comets, if you look there in their objectives for their future missions, it's exactly the same objectives, the same question we have put forward. And the new missions, and especially Stardust, which brought back a sample of Comet Wild, opened a lot of Pandora box of new questions which are not consistent with our understanding. And that still, it shows we have to learn more.
So I'm prepared for the unexpected, according to the quote from David Levy before.
Yeah.
And you know, the most interesting point with our space missions were questions which came back we never were able to ask.
So basically the mission
Will be
comes
will be
up
a
with the
surprise.
questions. Yeah, I mean, that's brilliant.
Yes, that's my conviction. Yes.
Yeah.
Maybe I could add something not really on the risk aspect, but a bit related. What happens near Earth? I mean, every night on a clear sky, you can see some meteors, some falling stars. And these have been observed for thousands of years. But there is a lot of these are not really understood. What is the composition? Where exactly do they come from? It is believed that those mainly originate from comets. And sometimes every year Earth passes through. So it is something that where you have direct experience. They are not really dangerous, at least not on the Earth. Maybe to spacecraft in orbit they are. But even there you can learn something from missions like Rosetta. So something that happens on Earth every day.
Now this is, of course, the whole mission is a huge effort, and it took some 25 years of preparations and plus the scientific evaluation that will follow once we get all the data. What exactly is the longevity of such a mission and also of the results that you hope to get from it?
The impact the mission will have will be, at least on science, it will be felt decades after. But it depends on my dear science colleagues that they work hard to analyze the results, do it jointly, and you know, this is a worldwide undertaking with all the cultures in there. And I'm pretty sure just if you go to the mission to analyze the results, will bring us a couple of years after the end of the mission. This is to analyze the data. But at the same time, it's not only the measurements we're doing. We have, as we mentioned before, you have to put it in the great context. You want to put comets in the context of the evolution of the solar system. Comets, perhaps in the context of the evolution of life. And that means that people have to work together. You take aspects from the different instruments, and we said that before. We bring a laboratory to a comet. And with the results we get, we will try to answer questions. We will get new questions, and we have to see if we can get a consistent picture of comets and the role comets played in our evolution.
So there's still a lot of work cut out, a lot of questions to ask, and hopefully lots of answers to find. And talking of which Q&A, of course you are in this session also invited to ask your questions. You can do them individually, of course, afterwards as well. But if you want to join the round now, then all I need is your hand up in the air, and you can fire away. I do not see a hand up in the air. No, I don't think so. Everybody is happy listening in. I have one more question, and that fits very well with our timing as well, because European Space Agency, Rosetta mission, it is a huge European effort as well. Many different nations are involved, many different organizations, even represented here on stage, some are involved. How easy is it to get all the cooperation sorted out? What was your experience? I mean, how easy to get, for example, the defense, space and Airbus Defense and Space involved in this whole process? What was your experience?
Okay, you can imagine organizing about or more than 60 industrial teams over a time span of about 10 years. That's quite a big effort. And you have to try to produce a common sense for the overall target of the mission. You do not need some person with its speciality, but you have to integrate all these nationalities and characters into a common objective. And I guess that's the major task for the project manager, which is here Dr. Best. Okay, yeah.
Yeah, it is a major task, but from what we've heard so far, it's sort of been successful up until now.
No, it has been very successful. It's really a European, it's Europe, so as it is, where people have to work together. In science, it might be sometimes a little more difficult, and my dear PIs might excuse what I say, but you have in science also a lot of prima donnas. Everybody is the best. Every instrument is the most important, and they have to get all the stuff, and you have
But that's the truth.
This is the truth, but you have to see that they have to work as a team, because, you know, there are 11 instruments on the orbiter. Everybody wants to get its share. In the end, we have to get the best out of the mission. So some are, as usual, more important than others, but in the end, everybody has to join the team and has to get it out, and they have to sometimes compromises, and that shows you have to, it's like in the circus with them as a wild beast there.
Yeah, and of course, what concerns is risk from near-Earth objects. That obviously is something that concerns the whole Earth.
Absolutely.
So it can only be done in international context, and that's also the way it's been done. So information that we get will be shared worldwide, and it can only be done in international cooperation. And perhaps I could even mention in 2.5 weeks from now, there will be a meeting here at ESOC where all space agencies are invited to form a group that addresses the risk and what potentially one could do. And the first meeting should take place here in 2.5 weeks' time.
Very, very interesting and very comforting. Please do keep an eye on near-Earth objects for us. Find a solution. Thank you very much, all three gentlemen. Good luck with the mission. Thank you very much for sharing all your knowledge with us. Thank you for your interest. And again, we'll be back here with the latest update from the main control room at 4:45. And Norbert,
you started with a classical quotation. I have another one for as a final word, you know.
Off you go.
It's from Mark Twain. He said, give the next comet in your life the chance to be the best.
Give the next comet in your life the chance to be the best. All right. But you won't argue with the fact that let's stick to 67p for the time being. You know, one comet at a time. That's all I can deal with at the moment. We'll be back again at 4:45 with an update from Andrea. Now there's a question. There's a question now. If you can make it very, very brief, because I've been told that we have to stick to those time slots. Okay, we can't hear. We can hear you, but everybody else can't hear you. But I could quickly translate it in order to save time. So, because we mentioned that the questions come with a mission, so what role did creativity with the team beforehand play in order to get that mission started?
First of all, you have to know comments, and you have to be creative to address questions, because you're building your instruments for that, and therefore you have to anticipate to some extent what you want to study. As it was mentioned, there will be a lot of new things coming up, which hopefully are there. And the people and the scientists are very creative. They are creative, also thinking theory, and they have to be falsified, and you have to show that it comes. And this will come in as soon as we have the data. You really will see that people work together to understand it and get new ideas, what it means. And that is necessary, and I can tell you, our dear science team is very creative there.
Yeah, I can vouch for that.
Yeah.
I've met quite a few of them. All right, if you have more questions, I'm sure everyone here will be happy to answer them individually. I have to call this a wrap now, and I will see you hopefully in an hour's, well, no, actually 45 minutes time from now. Okay. Thank you very much. Okay, I promised you an update from the main control room at 4:45. It is 4:45 now, and we're trying to establish contact again with the Rosetta spacecraft operations manager, Andrea Accomazzo, who I'm sure will be glued to the screen to see the signal when it arrives, as we were told earlier. Maybe we get the signal a tad earlier, even if that would mean a first for any of the ESA operations so far, or the signal will be here at 6:45. But Andrea is the one who would know all the details, and they're still trying to find Andrea. That's me, there he is.
Yeah, hi.
Andrea.
Hi.
You're smiling. What is the latest?
Well, we have successfully started tracking the position on the sky where the spacecraft is meant to be, and we are receiving no signals so far. The colleagues from the US that are supporting us in this operation are transmitting also live. The signal they are measuring is pure noise received in the receiver in the ground stations. They've also processed this data with an offline tool to really find out whether there's anything hidden, and there's absolutely no sign of Rosetta so far. So it's absolutely nominal.
But there are nominal is good. You mean no news is good news?
Indeed, this is what you may be even seeing on the screen. This is what they send us. Good news, no signal yet.
But there are more ground stations involved. I mean, which ground stations are the next to look for that sign?
Currently, we are tracking the spacecraft with the Goldstone ground station. It's located in California.
Okay, so we're still in the US. Mm-hmm.
In the US, right. Later on, the spacecraft will be visible, will start being visible from Australia. So we will start monitoring with still a US station position in eastern Australia, in Canberra. And then a couple of hours later, the spacecraft will be in visibility with our New Norcia station, Western Australia. So this occurs in the next hours. If the signal comes at the nominal time, we should be able to see it already from the California station, Goldstone, and we'll be the first one to pick up the signal. The other two kick in a bit later.
Okay, so when we speak to you again at 6:30, if the signal comes in when it is due, then we will still have about another 15 minutes to wait to receive the signal. Is that correct?
Well, this is if everything is absolutely nominal. We had no drifts of the clock, and the hibernation exit procedure today works exactly in the same way it has worked when we did the test in 2010. The sequence of action is not fully deterministic. That's why we also have a bit of uncertainty. There's an uncertainty a bit on when the clock will kick in. So the uncertainty is several minutes. We cannot nail it down to a few seconds.
Andrea, while we're waiting for this signal, what exactly happens next? Let's say we have the signal. Are we then just all drinking champagne and that was it? Or is there still something to be done?
Well, you are all authorized to do, but unfortunately we cannot do it on our side. We have a bit of time pressure to take a couple of actions. The spacecraft would take autonomously the decision to switch off the transmitter 5 hours later after we have received the signal. And we want to intervene and gain control of the spacecraft before this occurs. Otherwise, we lose a window. We'll have to wait another 7 hours to get it back. We don't want to lose this chance. We have to intervene immediately.
Okay, so the earlier the signal, the earlier you can call it a day and say, all right, now I'm ready for bed now. If the signal comes late, then you have to work late.
Absolutely, but okay. That's why we also split in 2 teams.
Very good. Well, Andrea, then keep up the good work. We look forward to checking in with you again at 6:30. Unless we hear anything else before, then of course we cross over first.
Okay, thanks. Talk to you later. Bye.
Okay, well now you know everything is nominal. we can all be very relaxed. I don't know whether there will be champagne later, I presume so. But before we get to that, we have another session coming up here with 3 very, very interesting scientists, of course, which will start in about 10 minutes from now. So stick around, and I'll see you in 10 minutes. All right, here we are again for our 3rd and last session this afternoon, and this time myself and those 3 gentlemen would like to focus on Rosetta and the Philae lander science, because you know that Rosetta, the orbiter, isn't alone. It carries a lander which eventually, hopefully, will land on the comet's surface and conduct some scientific analysis never done before. We'd like to talk about this now with, I start at the very far right, Professor Jean-Pierre Bibring. To my side, it's right. It's my right, it's your left.
Yes, but left and right depends on...
Let's just leave left and right completely out of it. The gentleman with the beautiful scarf is Professor Jean-Pierre Bibring, Philae lead scientist and Shiva principal investigator at the Institut d'Astrophysique Spatiale in Paris. Then next to him is Dr. Stefan Ulametz. He's the Lander project manager at DLR, which is the Deutsche Zentrum für Luft- und Raumfahrt. And right next to me is Dr. Wlodek Kaufmann, principal investigator and of the CONSERT instrument, something we'll be talking about, which is on board of the lander at the Institut de Planétologie et d'Astrophysique in Grenoble. So, having said this, and obviously we also need a round of applause for these gentlemen. We can't make an exception here. Thank you very much. So you've been welcome now. I would like to start with you, Jean-Pierre. First of all, we asked earlier why go to a comet in the first place. Now, the next question, of course, would be why send a lander there?
Well, the answer is in the question. We've been to comet far away. We know what a comet is because it's sublimate. There is a coma around. That's why we call it a comet. We never landed. What does that mean? We never could analyze the material themselves, the grain themselves, the sample themselves. We never could measure the properties themselves from there. And we are absolutely convinced that when we do that and when we correlate what we find there to what we'll do from the orbiter, then the entire reality of a comet will finally be revealed. For the moment, we really don't know what the material is, so we need to be there to analyze. Mm-hmm. And what we are bringing that is really a real laboratory with 10 instruments that will do there what we would have done if we had brought samples back to the Earth. We would like to analyze that grain per grain, sample per sample, to know what this material is made of. As you have heard today, we are absolutely convinced that this material played a key role in the evolution of the planet themselves, of the diversity. Earth is very different from the others. We still do not know how life started. We know there has been water. We sort of know how water went. Comet played a role. The big question is how the carbon went, in which form. Small molecules, big molecules, did they play a role? We just do not know. But we are absolutely convinced that the role was critical, and we hope that Rosetta will really help understanding that.
Mm-hmm. My question is then, what if this comet and being there gives us those answers to those questions you mentioned? What are we doing with these answers then?
We'll put that in the global scheme that we are building now on the evolution of the solar system itself. And, there is something absolutely new in the view we have of the evolution of the planet themselves. Even 20 years ago, or even maybe 10 years ago, we had no idea how to explain the diversity that we are seeing here. The Earth is entirely different from Mars, Venus, and the others, although we come from the same material, essentially. So what drives the evolution of the planets? How live there? Are we alone in the universe? What is the uniqueness of what we see here, the life itself? Is it unique at what scale? Within the solar system, the galaxy, the universe? Part of the answers in the ingredients themselves. The ingredients out of which the solar system evolved is key to the evolution afterwards. If you want to know the clues of the diversity as we see that now, we have to know the initial conditions. And comets are very specific to tell us, for the water and the organic themselves, in which form the thing started, and within this scape, we will know whether or not that's very specific to our solar systems or very generic in the universe. You know that when we compare our planets to the exoplanets now, we see the huge diversity. Not only the Earth is different from the other planets, but our system is different from the others. Why that? And that drive to the idea that maybe life is only here. Comets will serve the answers, not be the only, of course, of the answer.
Sure.
But that will be part of what we do with the other planets like Mars and others, to try to understand the reason why diversity is such that we are speaking here in that room now and probably nowhere else in the universe.
Okay.
Happens.
And in order to understand that, we have to touch the comet. We really have to be there.
Yes, because we need to know the material out of which finally it evolves when the sun modify that. Yeah. So the coupling between what we see inside the comet itself, even drilling samples, as you will see, subsurface samples, and then analyzing the transformation of this material from there to the orbiter and then possibly to the Earth, that will tell us what the material out of which we probably formed ourselves.
Why I'm persistent in that way is, of course, because I'm not sure, I mean, the whole Rosetta mission, you have the orbiter, the comet chaser, and now you also have the lander. Mm-hmm. Now, that combination, Vladek, perhaps you could tell me, was this combination conceived as such right from the beginning? Like, what was there first, the chicken or the egg?
I believe that this combination gives the possibility to do the measurements, let's say, in situ during the lander. We are sitting on the surface. We have direct measurements coming from this. And we have the measurements from the orbiter, from the remote sensing measurements, telling us what they see on the surface, how they analyze the gas, dust close to the surface. And we have also the remote in situ observation on the orbiter, measuring the same, or not exactly the same, because the parent probably, molecules coming to the space. There is one thing. We have also, with lander and orbiter, we have also the possibility to see the interior of the comet. Mm-hmm. Because all observation we have until now, and we are connected to the surface or to the coma, which means that we are measuring the gas outside of the comet or dust, or we are sitting on the surface, we are observing the surface, we are going, let's say, 10, 20 centimeters, perhaps a half of meter below the surface. But in order to see really the interior, the nature and structure of the interior, we need these two things, orbiter and lander, and we have there the concept experiment, which I will describe perhaps later.
No, actually, that would be a good point, because it is exactly this correlation between the lander and the orbiter that CONCERT explains really well, because this is an instrument in two parts, one which is on the lander and the other on the orbiter, and they have to work together in order to make it successful.
It's true, because we are transmitting the radio waves through the comet. Doing this, we learn what is inside the comet, like the people are doing the tomography or scanners in the hospitals. We are looking through the comet and we'll describe the interior. The question is, why to understand the interior? Because it's the first question which can come. Mm-hmm. I can tell you only two, let's say, very simple reasons. Firstly, the interior is a real fossil, real vestige of the comet. Because when the comet goes through the orbit around the sun, it's under the influence of solar wind, radiation, and these kind of things, which means that the surface is modified. Interior, not. Interior is real fossil since, let's say, few billions of years. We will see how it's built up.
Right.
And the next argument came to my mind when I heard the previous speakers talking about the mitigation. How do you want to mitigate if you don't understand how it is inside? We have to learn how is the inside of the comet. Of course, we have the models. We are building the models of accretion, of aggregation, etc. But we really don't know how it is inside.
How does, because if the inside is so important, how does the drilling of the comet and your tomography, the CONCERT instruments, how do they go together? Are they sort of doing the same job, in a way?
No, we drill a few tenths of centimeters. What we want is just to go what we call pristine material which have not been changed during the past 5 years, which have nothing to do with the 5 billion years, just because the sun was there. So, but the sun affects only a very, very tiny fraction of that. The idea that as soon as you go a few centimeters below the surface, the material that you have here is probably the same material that you had 4 billion years ago when it's created. So the drill is really that. Tomography is something different. You want to know the process by which the entire comet, which is some kilometers large, has been built and grown up, which is different in a sense. Yes.
Okay. Now, Stefan, we've been talking now about a couple of instruments already. You are actually the lord of the instruments. You coordinate 10 instruments on the lander.
With PIs like those tools, so you can imagine it's a challenge, yeah.
Yeah, well, that was exactly the question I was trying to get, to coordinate 10 instruments. It's not just that there are 10 different instruments, they also have different PIs in charge of them. They come from different organizations, even different countries that donated them, that developed them. How do you coordinate it so that it all makes sense?
Well, I was making a joke, it's a challenge, but indeed the lander itself is a contribution by not only France and Germany, but also contributions from Italy, from Hungary, from Finland, UK, Ireland, Austria. All these institutes brought certain pieces of hardware. So they did not just pay into a big pot, but they brought their little subsystems. And at the end, everything had to work together. And in addition, as you said, we have 10 PI instruments, each of them, again, having a complete science team, an international science team. So bringing this together was indeed not easy, but it also shows it's a very good example for a truly European cooperation, to have all these parties all over Europe working together and realizing the lander, and hopefully in November also the landing, and coordinate the data analysis and learn about comets.
All right, you're already way ahead. We're still waiting for the signal, but it's good to know what's yet to come. Now, we heard about CONSERT and about the necessity of drilling in order to get samples. I came across a name of another key instrument. It's called COSAC. Why is it a key instrument, or are they all key instruments, probably?
Well, one of the real key reasons to have a lander is to go to the pristine material, go to the comet nucleus, and analyze the material which has not been modified by outgassing or just measured in the coma. And COSAC is one of two so-called evolved gas analyzers. The other one would be Ptolemy, where samples taken from the drill will be fed into little ovens, will then be heated, and the gases will then be led by little tubes to mass spectrometers and gas chromatographs to really get the composition, the organic composition, also the isotopic composition, and really answer the key questions. What is this comet made of? What is the pristine, the original material of the solar system? This is something COSAC will address, with a special emphasis in case of COSAC on the organic chemistry.
Right. Because there is so much emphasis here now on really learning about the nucleus and what the inner part of the comet is made up of, in order to learn everything, or to answer the questions and the makeup of life and the universe. Does this mean, because you mentioned tomography, and you even mentioned hospitals, so I had to think of, so you check a patient, and of course humans are fundamentally, the makeup of a human being is the same, but then there are huge differences when you look for a certain illness, etc., etc. Does this mean when you check out this one comet, know them all? Or can we basically only turn around if everything works successfully and say, now we know 67P?
It's a good question. It's, for the moment, when we decided this mission 20 years ago, the idea that essentially in the solar system we have families of objects. Planets, giant planets, and comets were also a family. Afterwards, we discovered that families is really the way to sort of erase our ignorance. And planets has really different bodies, giant planets are different bodies. For the comets, we don't know. So for the moment, still consider that comets essentially are one or two families of bodies. So which one you take is not really important because they will essentially relate to the others. Is it true or not? We have no idea. We have no clue. So you might be right. After this mission, if there are many other missions, or even this mission might demonstrate that from one to the next, you might have differences. But the idea we have now of the process by which the comet formed and then evolved in a reservoir very far from, and so essentially unchanged up to now, demonstrates from the model at least, of the ideas we have, that they are much more a family than all the rest of the other family that I just spoke about. So in principle, when we chose this comet, it was not because it was specific in terms of the composition, because we had no clues of the composition, but only the trajectory, because it was just reachable, essentially. And we consider, and we still consider now, that it's a good candidate from that respect, because what we want is something which has preserved the composition in the outer solar system at the very beginning, and probably any body in the center, any object that would have preserved that would be identical in the sense that it will provide the same information of the material out of which we formed. So this is the answer I would give to you. The knowledge we have of the solar system now is that it's sort of, we don't care about which comet we have if it's well preserved.
Yeah. Now, I just would like to point out, of course, you've seen it already, that we actually have a model here of the lander here with us on stage. And I believe the scale is, what did you say?
1, 2, 3, 4.
1, 2, 3. So it is actually, it's not huge. Exactly.
One cubic meter, typically. So it's a big 1 cubic meter. It's 100 kilograms, so, you know.
And what it's going to do by landing on the surface of the comet is something that's never been done before.
No.
That could be very scary, a scary thought.
It is scary. It's not going to be. It is scary, and the risks are huge. But that's a good mission. I mean, we are trying to merge the ambitious scientific ambitions, trying to understand where we are from, and the challenge that goes with. But it's true that when we invented this mission long ago, we did not envision all what it would have cost in terms of the treasure of intelligence that the people here in particular put to make that happen. So it's true that it's much more complex than when we expected. And the risks are absolutely huge. We had to develop something supposedly to land on something which is unpredictable and unknown, and with very constrained resources. So we did our best to try to envision all the potential cases, but there might be entirely different realities. Sure. We might just seek when you are. If it's something like the crema catalana, which is very, a very thin layer on something we just go through and it's finished. We might miss the comet. If the comet is much more active, we'll never be able to go, as the image shows here, very close to and just be landed from very low altitude and that sort of thing.
So to a large extent, it also very much depends on the orbiter and how Rosetta functions.
And on the comet.
Sending
sure.
The lander off
but
at the right time.
The comet has to be cooperative. If the comet is cooperative, and we will know tonight, already, in a sense, we'll be successful. But the risk is huge.
When
you go back a little, when we designed the lander, not we because I did not participate, but I know the people who designed landers since the beginning, the discussion was how, what is the, where we land on the crust, or we land on the snow, how deep we'll go inside, how to build the landing gears to land this. And the value we gave was very, very different. For instance, this time we discussed, which means 20 years ago, about.
Well, the major fear we had when designing Philae was still called Rosetta lander those days, was a very hard surface and any kind of rebouncing. Because even if you bounce with a low velocity, it's fatal because you just disappear from the surface again. So we have all kinds of damping mechanisms, anchoring up on screws in the feet to protect us from rebouncing. Well, then the Deep Impact mission came, showing us more details on Comet Temple and some indication on the possibility that the surface rather may be a very loose regolith, very soft material. And suddenly the danger of sinking into the material was discussed, which I hope we will not sink very deeply because we compress the material, but now we...
So it wouldn't be bad to sink in a certain place because there's hardly any gravity.
Yeah, but still there is an inertia for the landing itself. So there is not weight, but there is the inertia of the lander. So we will compress the material. I don't think we will sink very deeply in. But the problem we anticipate now for the landing in regard to the surface properties have changed between the development phase and our current understanding. Exactly. And probably it will change again when we get the first images of Churyumov.
When you see the images of the comet, I think today it was shown 5 images, different comet. You see the diversity of this comet. And what Jean-Pierre said, of course, is very different because surface is very different. I hope that molecular analysis, elemental, etc., will show that it's probably good example of the cometary body.
Okay. I'll get to you, and then I will ask my wrap question because we are running out of time. Obviously, this is all, again, a fascinating topic, but I just need to check if there is an urgent question right now from you, because Q&As should be allowed. I cannot see a hand. Maybe I'm blind. But that's good for you, Jean-Pierre, because now you can say what you want to say.
Thank you. No, I just wanted to quote someone and to quote some people, because when you think of a system which is very clever, we have said for the orbiter, the lander originated in an institute which is not represented here. So I really want the people, some are in the room here. It comes from Max Planck Institute in Lindau. It was in Lindau, and with a brilliant guy, Helmut Rosenbauer, and he has his team. Some of them are still here. And most of the ideas on which we still will base the way we will land, or we might land, comes from there. The question of how the legs are, the rotation, whatever, is come there. So I think it's important to remember that these people are the key people out of that. Second, there are you have 10 instruments on board, and 2 people are supposedly responsible for that, what we call the lead scientist. One is from Lindau, and I think he's in a room, Hermann Bernhardt is here, so whoever wants to know something about the lander might also ask Hermann what it is.
Okay. Quickly?
Quickly, I want to add a small story of the landers, because at the beginning, when we start to build the Rosetta mission, it was planned to have 2 landers, one with NASA and one from Max Planck Institute, in fact. And finally, we terminated with 1 lander, because NASA withdrew.
But we made it.
We
still made it.
Yeah, sure.
Okay, then time is up. One last remark after all the precautions taken, and I'm sure that Philae will be a wonderful lander and carrying out great scientific analysis, giving us lots of data. But in the end, it's a kamikaze mission for Philae, isn't it?
Oh, I would not say kamikaze. No. It's certainly not the intention to die.
Well, but it won't return to Earth.
Well, it won't return.
Not in body.
We'll have a nice retirement on the comet.
A majority of mission is not returned.
It finds a new home on the comet. Let's think of it that way.
Let's put it that way.
Let's think of it that way. Well, thank you very much, gentlemen.
Thank you.
For telling us about Philae. Thank you very much again for your attention. And as you know, it's getting very exciting now. In an hour from now, yes, very much welcome. At 6:30, we'll be going back to Andrea, to the main control room. Maybe before that, we already have a signal, in which case we will let you know. And if not, then certainly see you here at 6:30.